So, sorry for keep you waiting. It's good that you have questions. That's a very good response. Of course, as well, I would like to apologize. It's a lot of material and not easy to understand if you hear it the first time. So questions are really welcome, and it's better to make it slower than losing too many of you here in the auditorium. Okay, great. We start with the questions.
You said you preferred measuring temperature using rotational modes, but seems like Raman spectroscopy mainly does it through vibrational modes.
Yeah, well, in Raman spectroscopy, as I said, you would need a very high dispersion to see really the single rotation line. So what you see is, in the end, with low dispersion, something like that. And it's questionable how well you can now resolve from this superimposed lines, which are smeared out, a good temperature. That is why you typically you don't do it unless you really have a high dispersion and you see single rotation lines that can easily fit it or more easily fitted, but that comes on the expense that you have a very low signal. If you have only, let's say, a microsecond to measure for your measurement because of the turbulence, then your signal will be very low. And maybe I haven't pointed out that clearly enough. These Raman cross-sections giving rise to this scattering process are extremely weak. So to give you an idea, maybe you need 10 to the 8 photons to create one Raman photon. And if you have low density, like in atmospheric gases, your signal is really, really low. And so that's why you cannot afford to disperse and bring your signal down. And what you say is now, okay, why not using the ratio between the ground and the first hot band? In principle, that can be done, yes. But then you do have only, let's say, access for temperatures above 500 Kelvin. And because you are very often interested as well in lower temperatures, that is why it's not a good choice. Yeah? But that, in principle, can be done, but still you would need here for the nitrogen still a rather high dispersion, and that kills your signal. And that's why it is not as appropriate. And that's why it's maybe a good point here to lead you over to a technique which provides much higher signals because of a directed signal, a nonlinear technique which is called Coherent anti-Stokes Raman spectroscopy, where you can afford to have a high spectral resolution because the process is so much stronger than the spontaneous Raman scattering. Okay? And that is what I have as plan now with the remaining half an hour or so to pass over the fundamentals of this nonlinear technique. It's not simple, and it's as well not simple to explain. I do my very best, and I guess I will fulfill that only partly your understanding, such that any questions are welcome. Let's get back to the explanation which we had in the context of Rayleigh and Raman scattering. So here it's expressed mathematically what is meant by a polarization. So this quantity pi means here that you induce a polarization by the action of an electromagnetic field that interacts with your molecules. Yeah, I try to explain that, where you have an electrical field that is changing in time, and that imposes a force onto your molecule such that the electron cloud and its orbitals is changing its position relative to the nuclei. This is an induced polarization. If you have low energy, low amplitudes in your field, E means here the electrical field amplitude, you do have a linear relation. A linear relation which goes over this chi tensor, which is molecule specific. Different molecules do have a different polarizability. That is a quantity that quantifies how easily you can remove or distort the electrons relative to the nuclei. If you have only loosely bounded electrons, this quantity would be higher. If they are very strongly bounded, you need a higher force to get them into motion. And so this is dependent on the molecule. And the first term here, that gives rise to Raman and Rayleigh scattered photons. Okay, and now we come to the point where we act with laser intensities and thereby electrical field strengths which are enormously high. So now we are talking about lasers which are focused and that provide intensities due to a very short pulse length, which are really, really high, such that you have to consider as well a nonlinear response. So that is generally true. Whenever you have your perturbancy by the electrical field in this case, which is high, you do not have only a response which is linear, but as well nonlinear terms. We refer here to gases, and you can show that due to symmetry reasons, this term with a quadratic term with a square here, that is 0 in gases. So the lowest nonlinear term is this term where you have here a cubic influence of the electrical fields. That's why you have here 3 electrical field components that create now a polarization which is not only linearly dependent on the disturbancy, but here responds with a third order. And that means this molecular property, this chi3 tensor, is here the important quantity which is molecule specific. Have a look at the ratio between these molecular specific quantities. There's a huge difference. To make this nonlinearity really observable, you have to overcome this small quantity by really high field strength. And that's why you can observe this nonlinear effects in optics only with pulsed lasers. So that's the first thing. Okay, later on you will see that this quantity actually contains as well the Boltzmann distribution. So what we try to measure is in the end this quantity which denotes the temperature. So any question about this, let's say this pictorial view of what is happening if you have a disturbant electrical field, how it drives the polarization? If that is accepted, then we can go further. And that is the next step. In electrodynamics, you can show if you do have a polarization, which is in our case now induced by this laser pulses interacting with the molecules, then this is the source of a new electromagnetic field. This causes what we then call later a Carr's signal. And you throw in here this term, put it in, and you go through something like 4 or 5 pages of mathematics, and you end up then with an expression, which is the only thing I can present over here, where you have, in this kind of spectroscopy, you shine in 3 lasers denoting these different electrical field components. In the end, we refer not to the electrical field components, but intensities. That's what we actually measure. So that's why I refer only to this equation, where you have then here a Carr's signal with a given intensity that nonlinearly depends on your 3 lasers that go in. For practical reasons, as we see in a second, you have 2 so-called pump lasers that have the same frequency. They go in with here the squared, and you have a second laser that is later on called a Stokes laser that comes in a second Y, where the intensity goes in linearly. Then you have here this chi3 tensor, which contains the Boltzmann distribution. You have the interaction length, which is going in as well squared, and another term that is shooting up here the first time in this discussion, a phase mismatching term that needs as well some explanation. So in the end, you measure that, Carr's intensity as a signal. You measure the intensity of your ingoing lasers. You know you try to minimize this phase mismatching term, making that to 1. You have a given interaction length such that your outcome is this quantity, this chi3 tensor, which contains the Boltzmann fraction. And that is then where we deduce the temperature from. Okay, and now based on that, I try to explain the process. So it's a nonlinear process where you mix 3 incoming laser beams. And first of all, we look at the energy balance. So what you do first, you shine in a first laser with frequency omega 1. Yeah? And if you would do spontaneous Raman scattering, then you would just wait that your scattered photon would return to, let's say, this first vibrational excited level. But this is not what you're doing. So you're not waiting for that as in spontaneous Raman scattering. What you do is, simultaneously to that photon, you shine in a second photon, with a frequency such that the difference between these two frequencies, I should give you now here the mathematics about it. If you take now the difference between these two frequencies, then this should be exactly the frequency of this, for example, vibration, or it could be as well a rotation. This is specific to a certain molecule. Later on it will be primarily nitrogen. So this process, shining in a laser with omega 1 and simultaneously with omega 2, you call Raman pumping. You're pumping here in this excited level. And that needs even more explanation. So you have to understand that in this process, omega 1, you can say minus omega 2, pumping this level, you create in this process another photon with omega 2 on the expense of omega 1, and the remaining energy, the difference, goes into, for example, the vibration. So after that interaction, let's say you shine in that for nitrogen molecules, your probe volume will show a coherent vibration of these nitrogen molecules. And as I said, omega 1 photon is changed into this vibration plus another extra, a new created omega 2 photon. And now, in cars, typically you don't wait. You directly shine in as well a third photon. And for cost reasons, you take the same laser, which is split into two beams, having the same frequency as the first pump. The second pump typically has the same frequency. And then from that on, you can observe, under certain circumstances to be discussed later, you can create now here the chaos photon. And this chaos photon, the intensity of this beam coming out of the probe volume, contains the number density from which you start the process. Here, the intensity of that beam contains the Boltzmann fraction. And this process is then very efficient only if you really have omega 1 minus omega 2 is hitting this resonance. If this is detuned and you do not hit a resonance shown by this dashed line, then this process is extremely weak. You can say it is in the noise floor. So only if this difference hits an Raman allowed transition, you do observe later on this Carr's photon omega 3. So this is, first of all, a brief explanation what is happening in terms of energy. Again, you have selection rules. The vibration state is allowed to change only by one. So for example, when we start over here, that is then, for example, V equals 0, and then you end up here in V equals 1. And most often we refer only to the Q branch, meaning that the J level is not well changing. So the J level is not shown over here. For rho vibration Raman, there would be as well J levels from which you would start this process. Here it is shown only for the vibrational part and not the rotation sublevels. Okay, any questions about that? Raman resonant and Raman non-resonant, weak and relatively strong. Now, there is coming something into play which we have not yet in the other techniques considered. We have considered only so far the energy balance. But you have to recognize that there is as well a momentum balance. So each photon contains as well a momentum. Momentum P given by the reduced Planck's constant and a wave vector. The wave vector from its modulus is simply 1 over the wavelengths. So it can be simply computed. So when we destroy here, when we consume a photon and create a new one, again, destroy a photon in this process and create a new one, you do not have to match only the energy balance. You have in nonlinear spectroscopy as well to balance the momentum. And that brings me to that important point that you cannot use simply 3 lasers and shine them in arbitrarily. You have to shine them in into a certain angle to each other to fulfill this momentum balance. So if you accept without any proof that any photon contains as well here a certain momentum given by its k vector, then we have here here this photon and this photon there by the process an additional one is created, then you must somewhere take the momentum from as well. So the momentum of the K3 and the momentum of the K2 photon here must balance the momentum of the photons that are used up, destroyed in this process. And therefore, you have to, this is termed, by the way, phase matching. And you have then different ways to do that. In gases, for example, you can do it collinearly. You can shine in the K1 and the K1 photons, omega 1, these two pump photons in one direction. And then you would see the K3, the Cars photon, and the additional Stokes photon as well in the same direction. That is not a good choice because then you have overlaid everything. You would not have any spatial resolution. That is why you take typically boxcars configuration where you have one laser, one of the pump lasers in this direction, the other in that direction, and you have chosen a certain angle. Then you have to choose corresponding to that an angle such that the momentum of this additional created omega 2 photon and the momentum of the additional created Cars photon, that they come up to the same value. Yeah? These are destroyed, these are created, the momentum is transferred from these photons to these photons. And that can be shown schematically like that. You have now your three lasers. You choose, according to the phase matching conditions, the positions at this lens, achromatic lens, such that you have the angles, such that this momentum balance is fulfilled. And then you will see that in a certain direction, you create the Cars photon. And because of this phase matching, these Cars photons, they have only one direction. Yeah? And that means all the information is contained here in a laser-like beam. It's not like in fluorescence, where fluorescence is taking place in all directions. The Cars photons, they have one distinct direction. And that is a very large benefit because you can collect them easily by one lens, even if this is relatively far away, maybe 300 millimeters, 400 millimeters, you do not lose any information. In fluorescence, because it's isotropic, you have to bring in your lens as close as possible. In Cars, it's not necessary. You can displace it from your probe volume by a couple of 10 centimeters. Okay, if you now use nitrogen to be probed, you use a YAG laser at 532, then because you have here a certain resonance from nitrogen, your Stokes laser has to be operated at 607 nanometers, and then you would create your raw vibrational Cars signal in the blue range at 473 for this molecule, for this choice of pump lasers and Stokes lasers. Okay? So this is as well easy to distinguish even if you have, let's say, scattered light that you could not prevent in your detector. You can easily separate it spectrally because it's really far off. Okay, any questions about this phase matching? This momentum balance? Maybe I should add something. Why didn't we care about this momentum balance in fluorescence spectroscopy? Because there as well, you have absorbed one photon. The energy is transferred to the molecule. It is destroyed, this photon. The molecule has to take the momentum of this photon. So that means it's only a small fraction. However, after the absorption, the molecule will have a different momentum. It is transferred as well to the molecule. And then the molecule emits a fluorescence photon. So the fluorescence photon takes not only some of the excitation energy, it takes as well momentum. And that means the momentum comes in the end from the molecule. It's changed in its velocity. It's relatively small, such that we can neglect it. But if you look carefully at it, it's not non-intrusive, yeah, because the momentum is changed. So Cars is one of the few techniques where you really, after the process here, you bring the molecule back exactly to the same quantum state as from which you started. And this is not the case in fluorescence. This is not the case in absorption. This is not the case in Raman. So you bring it back exactly to the same state from which you started. So this is really non-intrusive. Okay, there are now different ways to do that. So for cost reasons, you typically take a frequency doubled YAG laser as pump laser. And conventional Cars would use nanoseconds here. And then you can either scan the Stokes laser. That's why we typically take a dye laser where you can tune the wavelengths. And then you have these pairs of frequencies giving rise now to different Raman resonances. And now you go through the complete raw vibration spectrum. And that will be shown better in a second. That takes time. Scanning a dye laser over the spectrum takes minutes. So that is not applicable for turbulent flames. That's why in turbulent flames you use broadband dye lasers. Yeah, broadband dye lasers have no time to explain how they're working, but now you offer here a multitude of frequencies and wavelengths, and now you have all the pairs between pump and Stokes lasers giving rise to these different Raman resonances, such that your car's signal contains the full spectrum. And that can be done in a single shot. A single shot to pump photons, and here the broadband Stokes, and then you have in your car signal, as I said, the complete spectrum, which needs, of course, then a spectral dispersion, and that needs a high resolution. Now we are talking about the spectrometer, which is maybe a meter long, with a grading of 2,400 lines per millimeter with a high dispersion. And then you can calculate that spectrum. For nitrogen, we fully understand the spectroscopy. And so you can see here now, for 300 Kelvin, the raw vibrational transitions after spectral dispersion. And there is the rotation substructure not really easily to be seen. So for low temperatures, still it's not so good. But for higher temperatures, the next example I calculated is 1200 K. There you see here the spectra is broader because more J levels, more rotation levels are populated, and they shoot up very nicely. You can see them. And this is due to the transition from V equals 0 to 1. Then you see here the first hot band from 1 to 2, but it's not very strong yet because it's not really populated. Yeah? We have come back to that question you had. It's not really populated. That's why it's so weak. At 2,400 Kelvin, you see now the first hot band already is populated heavily, and the second hot band from 2 to 3 as well becomes visible. And all these small spikes are due to rotation levels. So you can now see in a single shot, later on it will show the measured spectra, you're able to see the raw vibrational spectra within a couple of nanoseconds. A very good temporal resolution. And if you now fit a theoretical spectrum to this complete bands, then you can be very precise. You're not only accurate because you rely on Boltzmann, you're as well very precise. Yeah, and so at least that's what you typically do. You fit a theoretical spectrum to the measured one, and what you change as a parameter once you have fixed all the other parameters going in, bandwidth of the lasers, dispersion of the spectrometer, and so on. There are a number of parameters that need to be fixed. Once they are fixed in a, for example, laminar flame, then actually you deduce the Boltzmann fraction and bring it back to the Boltzmann distribution. And so that is shown over here. Now that is performed in flames up to 2,500 Kelvin, but as well in areas where you have not any reactions yet. 284 Kelvin, you see here the measured spectrum in a single shot, within a couple of nanoseconds. Fitted to that is the theoretical spectrum with a parameter temperature tuned such that the residuum is approaching 0 for 950 Kelvin, for 1680 and 2100 Kelvin. You see very nicely that the theoretical spectrum fits the measured very, very accurately, and the precision with this type of lasers is maybe in the order of 2% at flame temperatures. And 2% precise in less than 10 nanosecond, it cannot be, there's no other technique which is better. Yeah? For lower temperatures, raw vibrational cars is maybe not the best choice. There are other choices like pure rotational cars where you do not change the vibration level, but that is only done in a few labs. And newer developments in cars as well go to shorter pulses, not only nanosecond pulses. There are developments in different groups where they have used ultra-short pulses, and then as well can increase the repetition rate. And they have shown as well that they can not only measure point-wise, but as well because of high intensities, they can do line measurements, for example. But the principle is similar to what I've shown over here. Okay, do you have questions?
Okay, with the broadband cars, does it still come off at a single angle, or does it come off at a range of angles?
The question is, when you do broadband cars, what is about the range of angles you have? Of course, if you do have different wave numbers, you need different angles. But because you focus, let's say with a 300 millimeter lens, you already have a certain extension at the lens, you have a certain range of angles anyhow. And that brings me, as a very good question, back to this expression over here. Delta K is the mismatch of this phase matching over here. And there's a certain allowance range where this is then this ratio, the sign of this phase mismatch over the phase mismatch is the ideal, of course, is 1. And if delta K, a certain mismatch will not make a huge difference. And so you will have these different angles, and even if you have a small mismatch, you have a certain contribution. Other questions? Yes, please.
Could you go forward one slide, please?
Yes.
All right. Why is it that when you shine the Stokes laser of frequency omega 2, you're enhancing the relaxation of the photon frequency omega 2? This is not an excitation, right? It's a relaxation.
This is you mean this process, bring it up to this virtual state and bring it down?
Yeah. Why does shining a laser like enhance like that relaxation?
Why that happens? That is, oh, okay, the question is, why this process here actually happens to bring it up and bring it down. So this is actually a 2-photon resonant process. That is, of course, only one possibility. Of course, you cannot prevent that another process takes place as well, but with less probability that you maybe make a frequency addition to a state which as well is not allowed, from which you have as well a relaxation maybe down to that one. Let's say something like a 2-photon excitation to a virtual state which is not allowed, from which it relaxed down to an allowed state. That will happen, but this probability is so much lower than this where you end up in an allowed state. It is, of course, still a process that needs high intensities, because the probability of that process being, and go back to this here, is very small. So you need high intensity. So most of the photons will not do that. But if you will do that, and those are then those from which you further on follow on your process. Yeah? And so if you would measure, if you would try to measure the number of photons that are destroyed, yeah? Let's say you take after the process here, you put a detector here, and measure the extinction of the green photons, you would fail. If you would try to measure the number of red or the Stokes photons which are increased, you would fail. So the process is really very, very unlikely. But the good thing is here, because the signal comes out as a laser-like beam, where all the information is collected within the spot, it is still very intense. Yeah? Although the absorption would not be easy to be measured. Yeah? But of course, there are limits. If you overstress it and you pump too hard, then of course it can happen that you make a Raman pumping, and here you would, if you put in too many photons, you can as well change the Boltzmann distribution here, but that can be easily seen. If you overdo it, then in your fit, for example, here, then you would not be able, if you drive it too hard, this Raman resonances, then maybe this first hot band would increase. And so that is as well something to be considered, that you match your intensities, that this is not happening. Yeah. Okay, other questions? As well from the CFD people. Okay. Okay, an application example comes later this week, so I will not follow up with that. I would like to discuss briefly the pros and cons. The advantage is you really have a precise single-shot thermometry measurement for nitrogen, typically, which is present in most of the combustion systems. You have a coherent signal such that the detector can be placed far away from your measurement or probe volume. And again, because you rely on the Boltzmann distribution in the end, there's no calibration required. Disadvantage, it's a relatively complicated optical setup. You need a pump laser, which is then typically used as well to pump the Stokes laser as second laser. You need to form 3 beams. These 3 beams have to intersect to fulfill the phase matching condition. And then, because they go typically through one lens, the overlap is relatively long. And so the best, at least, we could achieve with this kind of setups in these conventional cars was in the order of 0.5 millimeter. If you're interested in higher resolution, I refer to work by Chris Cleaver in Sandia National Labs. He is using a hybrid cars with ultra-short lasers, and he was able to reduce that by another order of magnitude. He was going down to 50 microns. But with conventional cars, that is a typical number. Very often you find here as well 1 millimeter or 1.5 millimeter, which is not sufficient to resolve the small scales. Perpendicular to that main beam direction, of course, because you focus it, it is maybe only 50 microns. And mostly it's a point-wise measurement technique, except of these new developments with ultra-short lasers, where we have as well seen 1D or even 2D cars applications. But that's the exception. Okay. Now the question is whether we stop over here. I think the time is over, and I would like to postpone that for tomorrow. And with that, I thank you for your attention this morning. And if you have any questions, maybe come down and we'll try to discuss them over here. Thank you very much.